Before we dive into the technical detail of temperature uniformity surveys and reporting them, I want to quickly run through some corporate slides just to introduce Datapaq to you, and Fluke Process Instruments, our parent company. So Datapaq's been designing and building profiling systems since 1984. We're the single largest supplier of profiling systems. And despite being part of a larger company, our team here in Cambridge are specialists in this area. It's all they do. We have mechanical, electronic, and software design all based here, and it's uniquely focused on profiling products. In 2007, the company was acquired, and we now operate as part of the Fluke Corporation, and our operating company is Fluke Process Instruments. That's the logo you see on the top right-hand corner of all these slides. And this was created by the bringing together of Ircon, Raytec, and Datapaq. Raytec and Ircon manufacture non-contact infrared temperature sensors. These are fixed sensors used in an industrial environment, not the small portable ones that everyone's measuring temperature with at the moment. Datapaq started out designing systems for the coatings industry, as that's where our founder came from, but we quickly expanded into other industries, and one of the first was metals heat treatment. Just to give you some idea of how we're based around the world. So, as I said, I'm based here at Cambridge in the UK, where we have our design team. Our manufacturing is done at the Raytec building in Berlin in Germany. Our Fluke head office is in Everett, which is in Washington State on the northwest coast USA, and we have sales offices on the east coast of the USA, and also in Shanghai, Singapore, and Mumbai, as you can see on the map here. And we are supported by a very wide network of industry experienced channel partners, some of whom have joined us this morning for this call. As I said earlier, we started out in industrial coatings, quickly expanded to sell profiling systems in the heat treatment area. And today's presentation is all around temperature uniformity surveys. And whilst I realize they can be done at low and high temperatures, they do fall into our furnace tracker product range. So the one with the red box around it there, high temperature heat treatment. So temperature uniformity surveys falling in this industry segment for us. Other segments that we're selling into are listed below, including ceramics, food processing, electronics manufacturer, and some very niche processes in the solar PV manufacturing industry. Okay, so we've done the corporate piece. As I said earlier, TUS is a fairly complex topic, and this is a rough outline of what I'm going to go through today. So a quick introduction to the products, and then talking about the placement of thermocouples and the difference between the working volume and the furnace volume. Looking at how the software can be used to make the report generation both easy and repeatable by storing data logger correction factors, thermocouple correction factors, and control specifications within the software. Now, these are operations that are done infrequently, so it's worth just reminding everyone how it's done and how best to use the software to get the benefit from it. And then when we come through to the end, we'll look at the report generation. We'll have a brief look at the differences proposed in AMS 2750 revision F. And then there's one slide that's not listed here on the contents, which is looking at some key differences between CQI 9 and AMS 2750. The two are closely related, but CQI 9 is the automotive standard, and there are some important differences just to call out. Products used in surveying furnaces. Data loggers, this is the heart of the system. This is measuring the temperature recorded by the thermocouples. Most often supplied with type K or type N thermocouples. They can also be specified with different thermocouples, and the image on the left-hand side of your screen there shows a 20-channel unit that has 10 type K, 10 type N, hence the changing color of the thermocouple sockets. So for for surveying different furnaces, you might have different thermocouple requirements, and this allows one data logger to be used in different applications. Thermal barrier range covers everything from low temperature composite curing through to high temperature vacuum processing with pressure gas quenches. So we have quench shields that can fit to the barriers to protect them through that process. Then we come to the right-hand side, the focus of today's presentation, the software that is used to make sense of all the data and how you can best use that to make TUS report generation as error-free as possible. Before we dive into the software, there's 2 or 3 slides now just on thermocouple positioning on the topic of working volumes and thermocouples to be used. The TUS is a process designed to show there's uniformity through the working volume of the furnace and that it meets the requirements of AMS 2750. Thermocouples used are generally mineral insulated. Most surveys are conducted with thermocouples with no heat sinks on the tip. And the wire frame diagrams here show some typical thermocouple layouts for a rectangular working volume and a cylindrical one. So for volumes in excess of 1/10 of a meter cubed, sensors are placed to measure the working volume. So we have 4 at the top corners, 4 at the bottom corners, and 1 in the center. For a cylindrical work zone, the sensors are placed at 120-degree intervals around the circumference at the top, middle, and bottom. And then another 3 sensors are placed on the center axes. Now, the topic of the number of sensors used is quite a complex one. It's not something we can get to in much more detail here, but suffice to say, in a static furnace, the number of sensors to be used depends on the furnace class and the working volume. So as volumes get larger, the number of thermocouples will become greater. And table 11 within AMS 2750 is the reference document for that. Our data loggers can support up to 20, which gets you to, that covers a significant proportion of the heat treatment furnaces. You know, there are composite applications on large aerospace sections where 2 loggers would have to be used at once, but the software is quite capable of merging those pack files to create 1 results file and 1 report. And this slide just shows something that most of you will be familiar with. This is a typical survey frame. So we can see that the working volume here is rectangular, despite this being a cylindrical furnace. It's quite normal. And we can see the thermocouples tied to the frame. The exit down at the bottom right-hand corner of the image there. This is going to be a survey that's done in real time. So the data logger is mounted outside of the process, measuring the temperature from those thermocouples that are typically tied to that frame with nickel wire. Moving on to continuous furnaces, and the topic gets more complicated. So there are 2 approaches to cylindrical furnaces. There's either a volumetric measurement or a plane approach, a plane method or swept volume. So if you imagine the plane on the left side there, proceeding through a conveyorized furnace, thermocouples placed in the corners, 1 in the center. As it goes through the furnace from entry to exit, it will sweep through the entire volume of the furnace, taking measurements as it goes. Our recommendation is always to place the data logging system behind the frame, the survey frame, so as we don't get any shielding or shadowing from the barrier, shadowing the thermocouples. On the right-hand side of the screen, you see there's some recommendations in terms of the number of sensors required relating to the height of the furnace. So less than 30 centimeters height, only 3 sensors are required, unless the belt width is more than 2.4 meters, then you start adding extra sensors. For furnaces above 30 centimeters, then you need to measure both top and bottom on the left and right. And the sensors up in the top corners have to be within 75 millimeters of the work volume. So it's quite a complex thing to build the frame to pass through the continuous furnace. The frame obviously has to have feet. It's going to stand upright as it's going through. Also, the sensors have to be within 3 inches of the edge of the working volume, so there needs to be care taken when placing the frame on the belt that it's actually centrally located. And photographs of the frame as it's going into the furnace will always be useful and can be incorporated in the report so that when you come to audit, you can show that you were correctly placed and measuring the working volume. Okay, so much for thermocouple placement. Looking at some of the software now. Remember, there are wizards in the software. Wizards are used to guide you through step-by-step processes that you don't do very often, just to ensure that every stage is completed before you move to the next stage. A typical application for wizards is something we used to do, which was buying airline tickets, where it steps you through each step of the process to ensure that everything's done. The wizards here, it's the same concept. We're stepping you through each of these processes. So the first one we look at is storing logger correction factors. When a Datapaq logger is calibrated by us, the calibration results are stored within the logger memory and can be automatically downloaded and stored by the software. And they're used to correct the readings from subsequent surveys. It eliminates user error that can occur when manually entering lots of data. If the data log has been calibrated by a third party, so typically an in-house calibration service or lab, the calibration will not be stored in the data logger. And in that case, the software wizard allows you can see that the screenshot on the bottom right, it allows you to enter the set points and to enter the calibration data so that that correction file can be stored. It's always worth doing this when the logger comes back from calibration, storing the results on the PC. Now, the Insight software will suggest a default directory. My advice would be that you create your own directory structure that makes sense to you. I would have a separate directory underneath my Insight that contained logger correction factors. This is something you'll be updating 3 monthly, typically, with a TUS system. All of the files are stored with an extension of LCF, so it's easy enough to find them. And you can fix the directories within the Insight software itself. It's well worth looking at the options and the help text on this to set up a structure that makes sense to you, rather than keeping a mixture of results files and correction factor files all in one directory. So we've dealt with logger correction factors. We now need to look at the thermocouples. The difference here is thermocouples can't store their correction factors, so there's no option to automatically download these. This is a manual data entry. The software wizard has been designed so that whether you have calibration for the entire spool of wire or for individual thermocouples, the data can all be entered, and you can enter either the measured results or the correction factors. So no matter what format the information comes to you, the software can deal with it and we can create this file. Use the notes boxes use the serial numbers, calibration dates, it's all there. Store it as these are delivered to you so that you have that data for future use. When it comes to report generation, you've merely got to recall this information and build it into the report. The software will auto-correct the readings once that's been done. And again, the same note applies. All of these files will be stored with a file extension of CAL. Just ensure they're organized, because if in the future an auditor is asking questions and you want to recall something quickly, it's much easier if you've got them all in one directory. Just click and recall the data very quickly through the Insight software. The Insight software does allow you to set up a controlling specification. This is an information field. It's not going to change the readings in the same way that the logger correction or the thermocouple correction does. This will be used by the software at the end of the process to advise the user which controlling specification class was achieved by the results. On the bottom of all these slides, there's some hints. I guess this one doesn't really apply. We would use degrees centigrade, as I'm sure all of you on this call are working in Celsius or centigrade. That was something for our American cousins yesterday. The tolerancing can be split, so that on the right-hand side of the screen, you see typically plus or minus 3, plus or minus 4, 6. You can have a different positive and negative tolerance. Just type the positive one in first and then go to the box on the right, type the negative one in if it's different. If they're both the same, go straight down the positive line, typing in, and it will be copied across to the negative tolerance. Okay, so that's the kind of pre-work. That's the stuff that will be done up front as the loggers receive from the calibration house and as the thermocouples are received. So that's been completed. We now move on to looking at how we would generate a results file. Just some images of some furnaces here. You can see the barrier in the middle there on the center picture does have that quench shield I was mentioning right up front. Makes it look a bit like a doghouse. It's the roof on it that just deflects the gas in high pressure quench applications. So setting up for a survey analysis. The wizard we're looking at here is called the new Uniformity Survey Wizard, and I've snipped it and put it up there at the top of the slide. The name's not quite right. This is really around the analysis setup. The first stage in the wizard will be asking you whether you're going to measure the furnace now or whether you're going to analyze an existing file that you ran earlier. Measuring now is typically something you'd do if you're running a telemetry. For the purposes of this presentation, we are analyzing an existing file. The next step would be to specify the set points. So what set points was the survey conducted at, and what was their tolerance? And at that point, you can see at the second of those two screen grabs, there's options to bring up controlling specifications you can browse and find. You can also select rounding of the results to ASTM 29. In addition, if this survey is if this furnace is regularly surveyed at the same set points, you can see there's a load and save as button on the right-hand side. This information is only ever entered once. You can save it in the software so you can recall it in the future. So repetitive surveys every 3 months, you don't have to enter all the data again, simply recall it and use it. And that's where the real benefit of this software comes. So having set the tolerances, we then look at the stabilization criteria, one of the most important aspects of the TUS software. So the software will automatically locate the stable periods that will be used for the survey. And here you can just select the method you prefer in finding that period. It could be that it starts simply a period of time after the thermocouples are in tolerance, or it could be that you want a subset of the thermocouples falling in tolerance, and you can even set a tighter tolerance on that should you want to start the period. And this is how the software will find those areas of stable readings at each of the temperature settings. It can be overridden later, and when we come to that, we'll talk about that again. Now you're going to be applying some of those things that were stored earlier. So thermocouple correction factors, you now simply recall which thermocouples you're using, and the software will be auto-correcting the readings to allow for the calibration data that you've got for the thermocouples. We can set up the software to check for overshoots. When we're checking something, or we have a survey file that's gone up to 1,000 degrees, and an overshoot is not going to be easily visible to the eye on the graph, because it will be maybe 2 or 3 degrees, and the software will check for that automatically if you've checked the box. You can see there's a number of options that are grayed out here. These would be alarms or alerts that you would actually use when conducting a real-time survey, and these would be able to alert the user when those stabilization criteria that we talked about on the previous slide have been met, enabling you to go from one set point to the next very quickly, or in fact in the shortest possible time, so saving time on surveys. Next step, we need to apply those logger correction factors. So we look at what logger was used on the run, apply those correction factors, and that will be bringing us towards the end of the analysis setup. And now we get to the bit where there's a bit more human intervention here. We set up the stabilization criteria. The software will be looking for these stable periods of readings at each of the set points that are the survey results, if you like. And the graph here shows that you actually have the ability to drag the survey period around, so you can put it into the best position to show the furnace in the best light. The software will automatically warn you if you drag the bars too close together, trying to get a good set of readings. The top graph there shows the time above the little white box is red, showing you that it hasn't met your stabilization criteria for a long enough time. Once you've set the stabilization data for each of the 3, in this case, survey settings, you have the option to move immediately to the report, or you can save at this point, and that you can see at the end of the blue arrow there, the wizard will drop down to a box on the right-hand side of the screen, and you can choose either to go straight to the report, or you can finish off with the analysis at that point. So the next slide, we'll be looking at the report generation. So this is a very important part of the TUS software. This is the stage where a really good report can be created. In all the stages of this wizard, you will see at the bottom of the screens, there is a print preview button. That's there to allow you to look at what your printed results will look at prior to printing. It's always a good thing to do. These reports are very big. Get them right before you start printing out and using lots of paper. So the first stage is to enter survey details. And some of those boxes are automatically filled, as you can see on the screen here. So start dates, start times, but there are boxes on there that you would need to fill manually. Our advice would be that the next survey due date would be a very good thing to fill on this box. As would the working volumes or work zone dimensions. You can see it's the second box from the bottom there within the survey details. And the compliance with box is a free field text. You can, if you've done a survey that meets maybe an OEM specification, so something in addition to AMS 2750, you can make notes of it here. To the right-hand side of the details, you can see there's add and remove buttons. These allow you to add extra fields to the survey details. Everyone uses the software slightly differently. If you have more data that you need to record at this stage, and remember the survey details is going to come out on page 1 of the report, it's the header. If there's something else important that you need to call out, you can add extra boxes, create a title, and fill in the value fields. And you can save it. So these details can be saved as a template for future recall. So the additional boxes, the auto-filled ones with dates and times will be updated, obviously, but you can save the structure that you're creating by adding these extra details boxes. The next step is to move on to the probe map. Well, probes or thermocouples, I tend to use both words interchangeably. I apologize for that. So this is a wireframe model showing where the thermocouples were positioned during the survey. You can see this is a rectangular working volume. Something to note here is that in addition to the wireframe or the photograph showing exactly where the thermocouples were placed, you can take pictures of the individual thermocouples very close up and store those and link them to the thermocouple. They will be printed on the report, and that's another really useful thing to realize, is that if you get a question when you're presenting the report in the future and there seems to be an anomaly in the data, you can look back at exactly where the thermocouples were placed, how they were tied in place for each of them individually, simply by clicking on them. So that's the probe pictures there at the bottom right-hand corner of that second wizard capture on the probe map, a very useful feature. A little bit more work in that you're taking more photographs, but it will save a huge amount of time in the future if questions come up around this survey. So what does the report look like? As I said, there we go. We've got the first 3 pages of a 22-page report. This is just an example. And as I said earlier, survey details come up as a header on that. And any fields you've added will be at that point. In addition, we have some signature boxes on the first page, pass and fails. In this particular example, there's been an overshoot on the first temperature setting. So we have a red box on there, a red alarm that would have been created because the user selected that option. The notes box is free field. In there, I would suggest any notes relating to the survey can be entered and stored with it. Second page, you can see what's here, the probe map. In addition, just to the right of it, a bit small to read, are the probe descriptions. So this would probably be serial numbers of the probes used. I would suggest that's the best way of doing it, so that you can always relate back to the calibration files that you've got for those thermocouples. Uniformity survey results, that is what it is. Page 3 is the numerical analysis showing the maximum and minimum temperatures during the stabilization time. There's maximum spread is shown in there, the hottest and coolest readings during that period for each of the 3 set points. Page 22 of the temperature uniformity survey report has the thermocouple correction factors, the logger correction factors, and the audit trail. 3 very important items when it comes to auditing what you did, in that you can check here or prove that it was done with a logger that was in calibration, that you applied the correction factors to the reading, and that you applied the correct ones. The audit trail will note, it's automatically noting any changes to the data that have been made since the data was downloaded from the logger. So if you apply correction factors, you've applied the wrong ones, you reapply some new ones, it will all be there in the audit trail, so you can review what changes were made to the data since they were captured. So hopefully that was useful. That shows you the temperature uniformity survey report. Some hints and tips there on the use of directory structures and the work up front that we all know we should do, but sometimes don't, in terms of storing correction factors prior to actually doing the surveys. The next slide brings us to a quick note around some differences. So Stuart read through AMS 2750 Rev E and Rev F without falling asleep. And look, here are some of the main differences that we spotted based on that draft document. I think the third bullet down, that will make a change to our software. So we will be changing our software and the way we report out the data. The 18 pages of the report that you didn't see just now on the previous slides were actually a printout of the temperature readings for each of the thermocouples at each of the stabilization periods. And looking at this change on RevF, we will be recording and reporting that data from a point 55 degrees below the set point so that we comply with RevF whenever it is released. You know, it's not released at this point. For continuous furnaces, there's been a clarification around work zone length or qualified work zone length. I would suggest, and we've put the clause number in there, that anyone with a continuous furnace needs to read that in more detail. To go through it here, we would double the time needed for this webinar. There's been an addition of some new thermocouple tables. That's not an issue for us. Datapaq can make the data loggers available with a wide range of thermocouples. In fact, we already have type T loggers in use. And there's been a clarification regarding use of wireless equipment, and it doesn't affect us in that the piece of equipment that needs to be sent back for calibration is the one with the analog to digital conversion in it. That is our data logger that contains the radio equipment. So continue as is. It's only the data logger that needs calibration, not the full wireless chain of receivers and transmitters. Final slide, looking at some differences between the automotive standard, CQI 9, and the AMS 2750. In many ways, these two standards or recommendations are similar. The key difference is that AMS 2750 is essentially about measurement of a furnace at set points to show uniformity. And the CQI 9 basis has some tables, so it doesn't classify furnaces in the same way, is what I'm trying to say. CQI 9, the classifications are based on the process that will be conducted. And there are a number of tables in the CQI 9 document that detail the frequency of the surveys and the tolerance requirements, for example, for aluminium heat treatment or for carburizing, and they would be different. So it's process-based rather than furnace-based. CQI 9 only requires the upper and lower temperatures to be surveyed, whereas the people working to aerospace industry will be surveying at every 330 degrees centigrade, so a number of steps between the minimum and maximum temperature. There is one area where CQI 9 is a little bit tighter than AMS 2750, and that's around the frequency of the readings. They're suggesting that you take a reading every 30 seconds, whereas you could take a reading every 2 minutes in AMS 2750. In my experience, most people are sampling a lot faster than this. This is the data logger sampling into what we're talking about now. And one note on the subject of continuous furnaces before we finish off for today is that in CQI 9, the requirement is that the thermocouples are within 50 millimeters or 2 inches of the edge of the working volume, whereas right back at the beginning of this presentation, I was mentioning that AMS 2750 continuous furnace thermocouples must be within 75 millimeters of the edge of the work zone. So there are some minor differences. The two are similar in many ways, but well worth bearing in mind. And I'm sure those of you that are using CQI 9 will understand only too well these differences. Thank you for your attention. I hope that all of you will have found at least some of what we've been through useful. Hopefully it will provoke some questions in the use of the software. Hopefully there are some tidbits there you can take away that will make your life easier in generating new surveys. Remaining, so we will we can take questions. And I think Ely is online and will be helping me out in that area.
Yeah, Eric is on the line.
Over to you. Eric, sorry. Eric is on the line.
So be free to send a question through the chat or the question table. We are happy to answer. Yeah. Is something okay? Rob, you have a question here. When should we use the volumetric versus method for continuous furnaces?
Now, when should we use the volumetric method for continuous furnaces? I might ask my colleague to answer on that one. So, Stuart, you have any experience of probe placement in the continuous furnaces?
Yep. Good morning. Good afternoon, everybody. You can use the volumetric or the plane method for continuous furnaces, but my suggestion would be that the volumetric method is only really useful for indexed furnaces, so pusher furnaces, rotary hearth, possibly walking beam. But wherever a furnace is truly continuous and the products pass through always moving, I would suggest that the plane method is used. It makes much more sense.
Does that answer the question, Eric? Is that
from my side, yeah, it's clear. Hope it's enough for the impact. If I don't get any reply back, sounds not. Maybe question about the thermocouple location here. What is the best method of recording thermocouple location?
As Rob mentioned in the presentation, the best way to record the location of the thermocouples is in the probe map area of the reporting section, and I would very much encourage individual photographs of the probe locations. It's worth noting that you probably need to be recording the furnace control thermocouple location as well, and potentially load thermocouple locations. If these are built into the report, you can record the locations of those furnace instrumentation thermocouples as well, and that's a very useful tool.
Thank you.
Any more questions? Don't be shy. Eh? It's a totally anonymous. Not hesitate to ask questions.
So I can see one here from, and I won't try and pronounce your name.
Yeah.
So it says, for the double chamber vacuum furnace with oil quench, can you immerse the logger / Datapaq in the oil? The answer to that question is, at the moment, no. There isn't at the moment a requirement to measure quench delay or quench rate within AMS 2750, although there are other specifications that do require that you measure that. If it's all right, if you could drop me an email, or we'll get in contact with you offline and discuss this further, because we do have some interesting innovations that we're working on. So
yeah, that's an area we're working on directly now. So very interesting question. Okay, well, I think if there's no more questions, I think I'll hand back over to Leonardo. Who will...
There was another question.
There's another one. Oh, sorry, I don't see the chat. That's okay.
Let's go ahead, Eric.
Where would you recommend recording the furnace PID settings on the report?
As Rob mentioned during the presentation, the PID settings could be recorded in the notes section of the report, but also in the survey details section. If you add another title, that's a good area for those furnace settings, and certainly control thermocouple insertion depth if you want to record that as well. That's where I would record that information.
So that was the area for the survey details where you could add extra fields that go along with the ones that automatically filled in around date and time. So that would put those settings in the header of the report. which I think is probably the best place for them.
So, and we've got one more question here that says, can you have a real-time measurement and transfer the data to outside of the furnace as the measurement is carried out? Yeah, so with our data loggers, we have an RF telemetry system that can be used to transmit the data in real time, and you can then use those alerts and alarms that Rob was discussing in the presentation to help speed up that survey and let you know when you've had your required duration at each set point for your stable period, your measurement period. Yes, that is possible.
Okay.
All right, I guess that we don't have any more questions.
Yep, I was just pleased about Stuart saying no, there's no more questions coming in, Leonardo, so I'll hand it back to you.
Okay, thank you very much, all of you, for attending, and Rob, Stuart, and Eric for the effort for the webinar. It was extremely interesting. Just a last thing, I will send the webinar recording and the slides to all people that attended in the upcoming days. Thank you very much for joining, and have a good day or evening, all of you.
Yep, thank you, and stay safe.